All right, today we're pulling back the curtain on the invisible instructions that literally run our digital world. They're like the secret recipes that make everything from your phone to the entire internet actually work. We're talking about computer algorithms.
Have you ever stopped to think about that? How your map app can find the absolute best route, avoiding traffic in just a split second? Or how a search engine can dig through billions and billions of web pages almost instantly? It feels like magic, doesn't it? But it's not. It's actually something way more impressive, a perfectly designed recipe.
And that's really the hero of our story today, the algorithm. It's the secret sauce, the fundamental concept that makes all of that digital magic actually happen.
So, what is it really?
Well, at its core, an algorithm is just a set of super precise instructions. You give it some information, that's the input, it follows a very strict sequence of steps, and then it produces a result, the output. The key here is that there's no guessing. It's an unambiguous, crystal clear path from a problem to its solution.
You know, the best analogy, and the one we'll keep coming back to, is a cooking recipe. Think about it. You've got your ingredients, which is like your data. You've got your instructions, preheat the oven, mix the flour and eggs, and if you follow those steps exactly, you get what you wanted, maybe a cake. An algorithm is the exact same idea, but its ingredients are data, and its kitchen is your computer. So let's look at a really simple recipe, an algorithm called sequential search. Imagine you're looking for one specific book in a big, messy pile. What do? Well, you probably start at the top. You pick up the first book and ask, is this the one? No. Okay, you put it aside, pick up the next one. You just keep doing that one by one until you find it. It's simple, it's logical, and it works. That right there is a basic algorithm in action.
Okay, but this is where things get really, really interesting. Because just like in cooking, not all recipes are made equal, right? Some are brilliant and fast, and others are just clumsy and slow. So we need a way to figure out which is which. You can think of it as the algorithm Olympics. So the big question becomes, is it a good recipe? Just having a set of instructions isn't good enough. That simple search method we just talked about, it's totally fine if you're looking through 10 books. But what if you were looking through 1,000,000 books or 1,000,000,000? All of a sudden, that straightforward recipe becomes painfully, impossibly slow. We need a way to measure how good it is before we try to use it on a massive scale.
And computer scientists basically judge them on two main criteria. First up is what's called time complexity. Sticking with our analogy, this is basically the total cooking time. How many steps does the recipe have? How long will it take? The other is space complexity. This is like asking how much counter space you need for all your bowls and ingredients. In computer terms, it's how much memory the algorithm needs to do its job. The ultimate goal, of course, is to be both fast and efficient with your space. Now, to talk about this stuff in a standardized way, there's a special kind of language, a shorthand, called asymptotic notation. You've probably heard of the most common one, big O notation. Now, don't get hung up on the name. The core idea is actually super simple. It's just a way of describing how an algorithm's performance gets worse as the problem gets bigger. It ignores the tiny details and focuses on the big picture, the rate of growth. And this table right here, this is why Big O is so critical. It shows everything. Look, for a tiny list of 10 items, the difference between a good, okay, and bad algorithm isn't a big deal. But watch what happens when we scale up to 1,000,000 items. The good algorithm takes what? Maybe 20 steps? Amazing. The okay one takes 1,000,000 steps. But the bad one? It takes 1,000,000,000,000 steps. That's the difference between an answer that's instant and an answer you'll literally never get. So if we know that this difference exists, how do we actually go about designing these faster recipes? Well, it all comes down to having a smarter strategy. Let's go back to our book search. That simple one-by-one method and big O notation, that's O of N. It's our OK algorithm. But what if the books were sorted alphabetically, like in a library or a phone book? You wouldn't start at the letter A, would you? Of course not. You'd jump to the middle, see if you need to go forward or backward, and in that one move, you've eliminated half the entire book. That's called binary search, and its performance, it's that lightning-fast O of log n, our good algorithm from the table. And the brilliant strategy behind binary search has a name. It's called divide and conquer. This is such a powerful idea in computer science. If you're facing a problem that's just too big, too complex to solve head-on, Don't. Instead, break it down into smaller, identical, more manageable pieces. Solve those little pieces and then put the answers back together. It's the secret behind so many of the fastest algorithms out there. So, to build these really elegant, really fast recipes, you need the right tools in your kitchen. And in computer science, that means you need to use the right data structures.
If the algorithm is the recipe, then these are the specialized tools, the mixing bowls, the whisks, the baking pans. Things like stacks, queues, trees, and graphs, they're all just clever ways to organize your data, your ingredients, to suit the task at hand. Choosing the right data structure is absolutely crucial for making an algorithm efficient.
So, why do we obsess over all this, right? Why does shaving a few steps off a recipe matter so much in the grand scheme of things? Well, because it defines the very boundary of what is possible with computers. One of the sources we looked at for this explainer puts it perfectly. It says the whole motivation is to be able to compare algorithms and, more importantly, to predict the growth in runtime. Being able to predict how a recipe will behave when you give it 1,000,000 or 1,000,000,000 ingredients, that predictive power is exactly what lets us build the massive systems we rely on every single day. And that's the takeaway here. This isn't just theory. This constant, relentless race for a better, more efficient recipe is precisely why your digital world feels so seamless. Every time you get an instant search result, every time your map reroutes in a blink, you are directly benefiting from decades of this incredible algorithmic innovation. So I'll leave you with this final thought. We have designed these incredible recipes that can beat grandmasters at chess and find a needle in a digital haystack the size of a planet. But what's next? What are the really big, messy, everyday problems, maybe in medicine or climate change or logistics, that are still out there just waiting for someone to invent their own elegant, efficient, and world-changing algorithm?